So we're back to our second vodcast, which will focus primarily on what we call hydrogen bonding. It's a misnomer because we call it a bond, but it's really a force. If you look carefully at the periodic table, you would find that these compounds, oxygen, sulfur, selenium, and tellurium, are all in the same group or family. And therefore, since they're all attached to hydrogen, you would expect them to show similar chemical and physical properties. Well, this is a graph that shows the impact of molar mass versus the temperature at which something would boil. And you would expect, as we move down, or I should say, tellurium's at the bottom, oxygen's at the top, but as you move, say, from the bottom up to the top of that column, that you would continue to see, projected somewhere over here, that water's boiling point would be fairly low. And yet, as you can see, it's actually quite high at 100 degrees Celsius. And the reason that we're able to explain some of these trends is due to a force called hydrogen bonding. Now let's take a look at the bottom one below that. These are all polar substances. These are also non-polar substances. And so these ones are showing a fairly good trend, but why is water way the heck off the chart with that anomalous, very high boiling point temperature? So when you look at what happens with water, water is able to have a force called hydrogen bonding. Now, of course, you have to have hydrogen in the chemical compounds formula. Secondly, it can only occur when you have the element nitrogen, oxygen, and fluorine, or fluorine. So I call that NOF. And these are all polar molecules to begin with, so there's some dipole-dipole interactions. But this is a special kind of interaction that happens right here where the red dots are. The red dots are not electrons. The red dots are symbolizing a force. And officially defined, it's when the hydrogen atom on one molecule, or maybe on a giant molecule, is attracted to unshared pair or pairs of electrons on another molecule nearby. But that molecule, both of them, have to involve nitrogen, oxygen, or fluorine. Those are the only three. And they're quite strong. You can have interactions between two identical molecules, such as water, or here in the case of ammonia, you have one unshared pair of electrons, or maybe between water and ammonia. So those are called hydrogen bonds, and they account for the very high boiling point that we saw on the previous slide of water itself. These three, sulfide, selenide, and telluride, cannot hydrogen bond, but water can. And as soon as you have a strong force of attraction between you and a nearby buddy, then your boiling points will be higher, and in water's case, so high that it allows water to exist as a liquid on the surface of the planet. You would expect that it would be something like this in the minus hundreds, and in fact it is not. So without hydrogen bonding, number one, life wouldn't exist as we know it, because water can't exist as a liquid unless it's able to hydrogen bond. And interestingly enough, what makes it able to hydrogen bond is that it's bent, not linear. And let's go back to even farther. Why is it bent? Because it has two unshared pairs of electrons. So little bits of nothingness that are not very locatable have a tremendous impact on the behavior and shape of molecules and the universe as we know it. Whenever you've had maybe the urge to get your water bottle chilled really fast, maybe you did like me and stuck it in the freezer and then forgot about it. Came back later on and found that it had exploded on you. Water is also interesting because when hydrogen bonding occurs, it makes, as it turns from a liquid into an ice crystal, so here's a close-up of what's happening inside this crystal, it makes the length or the distance between the two consecutive molecules larger. So water's unusual in that its liquid state is more dense, if I said this correctly, than its solid state. Or another way to think of it is, ice cubes float in liquid water. Its solid state is more dense than the liquid state, and therefore it will float. Another few things that are not mentioned in this PowerPoint that are very important, and I'm not sure why they don't show those anymore, is when you talk about the structure of DNA, The double helical molecule bends back in amongst itself due to hydrogen bonding across the base pairs. So that's a very important structure that allows us to zip and unzip these giant molecules that contain our genetic information. Other factors of hydrogen bonding that impact liquid water specifically is it has a high surface tension. And we'll take a look at those properties of liquids that are attributable to hydrogen bonding when we get to a future vodcast. I believe that is the end of our hydrogen bonding. Let's summarize our intermolecular forces. You might have, we're not going to look at bonding because we're only going to talk forces. You might have an ion dipole force where you have something ionic like potassium bromide and have it in water, and a polar molecule like water can dissolve a solid like ionic potassium bromide. If no ions are involved, and we're talking about polar molecules, you can have the kind of polar molecules that exist permanently. Hydrogen sulfide or methyl chloride have permanent positive and negative portions of the molecule because of differences in electronegativity. And so there could be dipole-dipole interactions. If you have a special kind of dipole that involves nitrogen, oxygen, and fluorine, then you can have hydrogen bonding when an unshared pair of electrons is attracted to a hydrogen atom nearby, or vice versa. And finally, remember, all substances have dispersion forces, and dispersion forces are a function of your molar mass, the size of your electron cloud, and the polarizability of that cloud. We will continue later on in this chapter discussing how these forces can impact physical properties.